before Earth had oceans, before the sun had fully gathered its planets. Two dead stars may have collided in the darkness and forged some of the gold, uranium, platinum, and rare elements that would one day become part of our world. In this quiet journey, we follow neutron stars as they spiral together, tear open matter at nuclear density, and scatter heavy atoms into space on the edge of a newborn black hole. Thank you for spending your time here tonight. If this kind of calm science storytelling helps you relax, learn, or drift into deeper wonder, please like the video, subscribe to the channel, and share it with someone who loves the mysteries of the universe. And before we begin, what time is it where you are watching or listening from, and where in the world are you tonight? Leave a comment below. Now, let us step softly into the collision where gold is born from chaos. Carl Sagan's phrase about star stuff endures because it gives human matter a cosmic biography. It says that the atoms inside skin, bone, blood, stone, ocean, and metal were not placed into the universe ready-made. They were assembled. They passed through furnaces, collisions, radiation fields, and the long patience of interstellar clouds before they became part of Earth. For a long time, that idea seemed already large enough. The familiar story placed the origin of ordinary matter inside stars, where hydrogen burns into helium, helium builds carbon, and later generations of massive stars press their interiors into layered shells of heavier elements. The universe becomes a slow factory of matter, with each star adding something to the chemical memory of space. But the most precious and most difficult elements do not fit neatly into that peaceful image of stellar burning. Gold does not emerge in any simple way from the steady heart of a star. Uranium is not an ordinary ash of fusion. Platinum, europium, and many of the rare heavy atoms that give planets their hidden mineral character require conditions so extreme that the word furnace becomes too gentle. Their birth is not only a story of heat, it is a story of pressure, collapse, neutron flood, and escape. The deeper version of the star stuff idea is therefore stranger than the famous phrase first suggests. Much of the visible world may be starlight condensed into matter, but some of its heaviest traces appear to have been forged when dead stars struck each other at nearly unimaginable density, when space itself rang with gravitational waves, and when the debris of a collision began to cool into atoms that could later settle inside worlds. A neutron star is already an extreme answer to the question of what matter can survive. It is the collapsed core left behind after a massive star has ended its ordinary life. In such a remnant, gravity has crushed matter beyond the familiar rules of planets and laboratories. Protons and electrons have been pressed together until neutrons dominate, packed into a sphere only the size of a city but holding more mass than the sun. A spoonful of such material, if it could be separated and held, would outweigh mountains. Yet the comparison is imperfect, because neutron star matter is not simply heavy in the everyday sense. It exists because gravity has forced atomic structure inward until the boundaries between nuclei and surroundings almost lose their meaning. This is matter resting near the edge of a deeper collapse, too much additional mass, and the remnant can no longer remain a star at all. It becomes a black hole. For a single neutron star, that tension is almost static. It rotates, cools, emits radiation, and may carry magnetic fields of ferocious strength. For two neutron stars in orbit around each other, the tension becomes a clock. Their motion is not perfectly free, according to general relativity. A compact binary system loses energy through gravitational waves, ripples in the fabric of space-time. These waves carry away a little orbital energy with each revolution. The stars draw closer, their path tightens. A system that may have survived for millions or billions of years begins to hurry only at the end. as the orbit shrinks and the final approach turns gradual decay into sudden violence. The significance of that final collision is not only that it is bright, powerful, or rare. Its importance lies in what it does to matter. Stellar fusion has a natural direction. It tends to release energy as lighter atomic nuclei combine into heavier ones, but only up to a point. Around iron, the balance changes. Building still heavier nuclei by ordinary fusion no longer pays energy outward in the same way. The star cannot simply keep climbing the periodic table by burning one element into the next. The road that makes carbon, oxygen, silicon and iron does not extend smoothly into gold. Something else has to happen, and that something must overcome the resistance of atomic nuclei. Heavy elements require additional neutrons to be added rapidly, under conditions where nuclei can grow before they fall apart. This is why neutron-star collisions matter so deeply to cosmic chemistry. They begin with objects already made mostly of neutrons. When their surfaces tear, splash, stretch, and eject material during merger, they expose matter to an environment where neutron richness is not a minor feature, but the central fact. In that debris, atomic nuclei can capture neutrons faster than they can undergo radioactive decay. The process moves far from the slow, orderly image of stellar fusion. Nuclei become swollen with neutrons. Some of those neutrons later transform into protons through beta decay, shifting the identity of the element itself. In this way, matter can climb into the realm of gold, platinum, uranium, and beyond. The path is brief, unstable, and violent, but it leaves behind atoms that can endure for cosmic time. For decades, supernovae seemed the natural place to look for such creation. A massive star explodes, its core collapses, its outer layers are thrown outward. Neutrons appear in abundance. The setting seems ideal at first glance. It is one of the universe's great dispersal mechanisms, able to scatter newly made material into interstellar space. Yet details can weaken a beautiful story. As models improved and observations sharpened, ordinary supernova became less satisfying as the dominant source of the heaviest rapid neutron capture elements. The right conditions appeared difficult to maintain in sufficient quantity. The observed enrichment of heavy elements does not always follow the simple expectation that frequent supernovae should explain most of them. The question did not disappear. It changed shape. If the galaxy contains gold, europium, uranium, and other heavy elements, and if ordinary stellar burning cannot make them, and if many supernova models struggle to eject enough of them, then another forge has to be considered. Neutron star mergers had long been suspected, but suspicion is not the same as evidence. The turning point came when gravitational wave astronomy began to listen to the final motion of compact objects directly. When a pair of neutron stars merged in a distant galaxy, the space-time signal was followed by light. Telescopes across the world saw an expanding glow known as a kilonova, a transient event powered in part by the radioactive decay of freshly made heavy elements. This was not merely a flash beside an abstract calculation. It was a visible trace of new matter cooling after an extreme cosmic collision. The colours and fading pattern carried the imprint of neutron-rich debris. The event did not prove every detail of cosmic chemical history at once, but it made the case suddenly more concrete. Heavy elements were no longer only inferred from old stars and solar system material. They were connected to a source observed in the act of making and ejecting them. Gold, in this view, is not just rare because human beings value it. It is rare because the universe requires extraordinary circumstances to create it. The metal's chemical stability and warm shine on Earth hide an origin in unstable nuclei and violent expansion. before an atom of gold can rest in a riverbed, a vein of rock, or a human artifact. Its nucleus may have passed through a moment when neutrons arrived in a torrent, and decay transformed excess into identity. The same can be said for many elements that seem quiet once incorporated into a planet. Rare earth metals that help shape modern technology, radioactive elements that warm planetary interiors, and trace atoms that play roles in biology all belong to a deeper history of stellar death and redistribution. Their present calm is misleading only if calm is mistaken for simplicity. Matter can become ordinary after an extraordinary beginning. The Earth did not form beside a neutron star collision. It formed later, inside a molecular cloud enriched by previous generations of stars and explosions. The young solar system inherited what the galaxy had already mixed into its gas and dust. Some of that inheritance came from many older events, blended over immense time. Some may have come from a comparatively nearby neutron star merger before the Sun formed, close enough and recent enough for short-lived radioactive isotopes to leave a measurable chemical memory in ancient meteorites. This connection gives the story a strange intimacy. A collision between compact stellar corpses, occurring before Earth existed, may have contributed atoms that later became part of rocks, oceans, machines, and living tissue. The scale is enormous, but the evidence can be small, preserved in mineral grains and isotope ratios rather than in spectacle. This is the new weight carried by the phrase star stuff. It no longer points only to the glowing interiors of ordinary stars. It also points to the crushed remnants of stars, to binaries spiraling inward through gravitational radiation, to kilonova fading from blue toward red as their debris cools, and to unstable nuclei decaying into the elements that make planets chemically rich. The old statement remains true, but it has become sharper. Human matter is not only the ash of ancient suns. Some of it is the settled residue of collisions so dense and brief that their main signature passes through the universe as a ripple in space-time. The story begins with stars, but it does not end in their quiet burning. It leads toward the iron boundary, where fusion reaches its limit and the universe must find a more violent way to build the heavy atoms that later seem so still. The iron boundary is not a wall that matter sees, but it is a real limit in the energy accounting of stars. Inside a massive star, fusion works because some combinations of lighter nuclei can form heavier nuclei while releasing energy. That released energy is not a minor byproduct. It is what helps the star resist gravity. It becomes pressure, motion, radiation, and heat, all woven into the balance that keeps the star from collapsing too soon. Hydrogen fusion begins the long sequence by making helium. Later, if the star is massive enough, helium can build carbon and oxygen. Still later, deeper and hotter layers can assemble neon, magnesium, silicon, sulfur, and other elements in a structure often compared to nested shells. Different depths reach different temperatures and densities, so different nuclear reactions become possible in different regions. Near the end, a massive star can carry a layered interior, with lighter fuels burning farther out and heavier products gathered nearer the centre. This picture has a quiet order to it, but it is the order of a system under growing strain. Every new burning stage is shorter than the one before it. By the time silicon burning begins in the deepest region of a very massive star, the clock has changed from long stellar patience to something much more urgent. The core is racing through its last available sources of pressure. What matters for the origin of the elements is that this sequence does not climb forever. The curve of nuclear binding energy gives the reason. Binding energy is a measure of how tightly protons and neutrons are held together inside an atomic nucleus. When lighter nuclei fuse into products that are more tightly bound, energy is released. This is why stars shine. but near iron and nickel, nuclei reach a region of exceptional stability. Building elements heavier than this by ordinary fusion generally requires energy rather than giving it back. Iron is not valuable to the star as fuel. It is more like ash, a product that has no easy way to help support the core against gravity. This changes the meaning of a massive star's final interior. The formation of an iron-rich core is not simply another stage in a productive chain. It is a sign that the chain is approaching failure. The core can grow as silicon burning adds more iron group material, but it cannot burn that iron in a way that releases useful energy. Gravity continues to press inward. Electrons are forced into states of higher and higher energy, eventually, under extreme conditions. Electrons and protons can combine to form neutrons and neutrinos, removing pressure that helped hold the core up. Collapse begins not because the star runs out of matter, but because the matter has reached a form that no longer pays the star back. The iron boundary therefore separates two kinds of cosmic creation. On one side are elements made by fusion in stellar interiors, built through the long struggle between heat and gravity. On the other side are elements that require a different logic: gold, platinum, lead, uranium, and many rare earth elements do not arise as ordinary fuel ash. Their nuclei contain many protons, and that creates a difficulty. Protons carry positive electric charge, and like charges repel. The more protons a nucleus has, the harder it becomes to push another charged particle close enough for the strong nuclear force to bind it. The universe needs a way around that resistance. Neutrons provide the way. A neutron carries no electric charge, so it can enter a nucleus without being repelled by the positive charge of protons. If an environment supplies free neutrons in great abundance, existing nuclei can absorb them. At first, this changes the isotope, not the element. An isotope is a version of an element with the same number of protons but a different number of neutrons. Yet an unstable neutron-rich nucleus can undergo beta decay, a process in which a neutron transforms into a proton while emitting an electron and an anti-neutrino. When that happens inside the nucleus, the element changes, because the number of protons has increased. In this way, matter can move upward through the periodic table without needing ordinary fusion to force charged nuclei together again and again. Neutrons enter quietly, avoiding the electrical barrier. Radioactive decay then rearranges identity from within. There are two broad ways this can happen in nature. In the slow neutron capture process, nuclei absorb neutrons over long periods inside certain stars, especially evolved lower mass stars. If a captured neutron makes the nucleus unstable, there is usually time for beta decay before another neutron arrives, but it cannot explain everything. Some of the heaviest neutron-rich isotopes require a faster route, one in which neutrons arrive so densely that nuclei capture many of them before decay can catch up. That is the rapid neutron capture process, the R process, and it belongs to environments of far greater violence. The important word is rapid because the race determines the result. If decay happens first, the nucleus steps gradually toward a new element near stability. If neutron captures happen first, the nucleus is driven far from the stable forms usually found in matter. It becomes swollen with neutrons, pushed toward strange, short-lived arrangements that can only exist while the flood continues. Then, as the environment expands and cools and the neutron supply thins, the unstable nuclei decay back toward more durable forms. Along the way, they create a spread of heavy elements. The calm periodic table hides this history because stable atoms do not show the violence of the path that made them. A gold atom at rest in a mineral does not carry a visible scar from the neutron storm that formed its nucleus. Its electrons arrange themselves according to chemistry. Its nucleus holds together in silence. Yet the number of protons inside that nucleus implies an origin story beyond ordinary fusion. It says that at some earlier time, a seed nucleus was placed in an environment where neutrons were more available than almost anywhere in ordinary stellar life. The seed may have been iron or another nucleus already made by previous stars. It didn't have to begin as gold. It had to survive a sequence of captures and decays that change both its mass and its identity. That distinction matters because it turns heavy element formation from a simple ladder into a branching path. The universe does not build every element by adding one charged brick after another. It sometimes builds excess, then lets instability settle into form. The iron boundary also helps explain why heavy elements are scarce. The universe easily makes hydrogen and helium. Stars steadily make carbon and oxygen, and massive stars contribute many elements up to the iron group. But the conditions that make the heaviest nuclei are rare, brief, and selective. A suitable rapid neutron capture site must provide a tremendous density of free neutrons, enough seed nuclei, high temperatures, rapid expansion, and a way to eject some of the finished material before it is trapped or destroyed. Too few neutrons, and the process stalls. Too much trapping, and the new elements never join the galaxy. Too much disruption of the wrong kind, and the nuclei may be broken apart before they can settle. The problem is not merely making heavy nuclei for an instant. The problem is making them in a form that survives and escapes into space. This is where the earlier story of supernovae begins to look less complete. A core collapse supernova seems at first to offer nearly every ingredient collapse: neutrinos, shock waves, hot matter, and a newly formed compact remnant. It is natural that generations of models place the R process there. But the iron boundary itself teaches caution. Extreme conditions are not enough. The conditions must be extreme in the right way, with the right neutron richness and the right outflow history. A supernova can be violent without being a perfect heavy element forge. It can scatter oxygen, silicon, iron, and nickel while still struggling to supply the full pattern of gold, platinum, europium, and uranium observed in old stars and solar system material. The question is therefore sharpened rather than solved. Once fusion reaches iron, the star has delivered matter to the edge of one creation method. Beyond that edge, the universe needs neutrons in excess, and an escape route for the nuclei they transform. The heavy elements are not simply the next products in a familiar sequence. They are the result of matter taking a more indirect passage, through instability, decay, and environments where the normal calm of atoms is briefly undone. That is why the origin of gold leads away from ordinary stellar interiors and toward rarer events where neutron-rich material can be torn loose. The iron boundary does not end cosmic chemistry. It marks the place where chemistry must become stranger. The R process begins where ordinary patience fails. A nucleus sitting inside a neutron-rich outflow is not waiting through the long rhythm of stable stellar chemistry. It is exposed to a crowd of free neutrons moving through matter that has been torn from a compact remnant, heated, expanded, and pushed far from the familiar conditions of planets or stars like the Sun. Because neutrons carry no electric charge, they do not face the electric repulsion that keeps charged nuclei apart. They can be absorbed into an existing nucleus with startling efficiency when the surrounding density is high enough. At first, this does not create a new element. It creates a heavier isotope of the same element. A nucleus with the same number of protons but with more neutrons packed into it. The change may seem small in definition, but under merger conditions it becomes the opening of an entire path through the periodic table. If another neutron arrives before the nucleus has time to decay, and then another, the nucleus can be driven into a form that would be almost impossible to maintain in calmer environments. It becomes overloaded with neutrons, unstable and temporary, yet still part of the route by which lasting heavy elements appear. The pressure of the R process is therefore not only physical pressure, though the physical setting is extreme enough, it is also temporal pressure. The nucleus is caught in a race between capture and decay. In a slow neutron capture environment, the nucleus usually has time to adjust after each capture. If instability appears, beta decay can change a neutron into a proton, moving the atom one step upward in element identity before the next neutron is added. The R process does not allow such orderly spacing. Free neutrons arrive so rapidly that the nucleus is pushed far from the valley of stability, the region where long-lived isotopes normally reside. It is carried outward into a landscape of exotic nuclei, many of which exist only briefly before they break down toward more stable arrangements. For a moment, the matter is not moving along the stable periodic table known from chemistry. It is travelling through a hidden, unstable version of nuclear geography, one that laboratory experiments can only partly reconstruct and that astrophysical models must infer from signals left behind. That hidden route matters because it determines what the universe can make. A nucleus cannot simply accept unlimited neutrons. Nuclear forces have limits. At some point, adding more neutrons becomes difficult or impossible, and the path bends through decay, fission, or further capture depending on the conditions. In very heavy nuclei, fission can split one large nucleus into smaller fragments, feeding material back into the process and shaping the final abundance pattern. Some nuclei become waiting points, places where capture slows and decay must occur before the path can continue. These pauses influence which elements become common and which remain rare. The observed pattern of R process elements in ancient stars and in the solar system is therefore not a random scattering of heavy atoms. It is a fossil record of nuclear traffic under extreme conditions. Peaks in abundance can mark regions where the process lingered. Scarcity can mark routes where nuclei passed quickly or where survival was difficult. The periodic table becomes less like a static chart and more like the cooled residue of a storm. What makes neutron star mergers so powerful as candidate sites is that they begin with matter already rich in neutrons. In a neutron star, pressure has crushed atoms until ordinary atomic identities are largely gone. The material is not simply iron, carbon, or oxygen packed tightly together. Much of the star is an ocean of degenerate neutron matter, with a thin crust above more exotic layers. When two such objects approach each other, tidal forces can strip material from their outer regions, while the collision itself can launch hot debris into space. Some of this matter is astonishingly neutron-rich. Once it leaves the stabilizing pressure of the neutron star, it expands, cools, and transforms. Free neutrons become available to nuclei. The R process turns on, not as a gentle reaction sequence, but as a cascading rearrangement of matter that may last only moments before the outflow has thinned too much for further captures. The brevity is part of the power. The newly forming nuclei do not need a long stellar lifetime. They need an intense neutron flux and enough time, measured in fractions of a second or seconds, for capture to outrun decay. Beta decay then becomes one of the great translators of this chaos into chemical identity. A neutron inside an unstable nucleus changes into a proton, releasing an electron and an antineutrino. With that one internal change, the nucleus moves to a new element. Because element identity is set by proton number, the atom climbs the periodic table from within. This process repeats across many unstable nuclei as the debris expands. The outflow begins as neutron-rich matter near the edge of collapse and ends as a mixture of heavy elements moving outward through space. Some nuclei decay quickly, others remain radioactive for thousands, millions, or billions of years. Some become stable isotopes that can persist long enough to be folded into later stars, planets, meteorites, oceans, and living tissue. The R process is violent in origin, but its results can become geologically quiet. A speck of gold in Earth's crust is a final, stable answer to a sequence that once involved nuclei too unstable to last even a human breath. The process also releases energy. As freshly made radioactive isotopes decay, they heat the expanding debris. That heat powers part of the visible glow of a kilonova. The light from a neutron star merger is therefore not only the fading heat of impact, it is the afterglow of nuclear assembly, a signal from atoms becoming less unstable. The debris cools as it expands, but radioactive decay keeps feeding energy into it. Heavy R-process material, especially elements in the lanthanide group, can strongly affect how light escapes, absorbing and reprocessing radiation in ways that make the glow redder and longer lasting. The colour of the transient event becomes a clue to the composition of the ejector. Light, in this case, serves as a messenger for nuclear history. A telescope does not see individual gold nuclei being born, but it can measure how the expanding cloud changes brightness and colour, and from those changes infer that heavy neutron-rich elements are present in abundance. This is a delicate inference, but it is not empty speculation. It is grounded in nuclear physics, radiative transfer, and the comparison between models and observation. The difficulty lies in the fact that the R process does not occur under laboratory conditions that can be fully reproduced on Earth. Many of the nuclei along the path are too short-lived or too neutron-rich to be studied easily. Their masses, decay rates, fission probabilities, and capture behaviour must often be estimated or measured at the edges of experimental reach. Small uncertainties in these nuclear properties can shift the predicted abundance of the final elements. Astrophysical uncertainties add another layer. The exact amount of material ejected by a merger depends on masses, spins, the stiffness of neutron star matter, the formation time of a black hole, the structure of the accretion disk, and the behaviour of neutrinos and magnetic fields. The process is therefore known in principle and still difficult in detail. It is a rare case where the broad story has grown stronger, while many of the internal pathways remain unsettled. This unsettled state is part of why the discovery of a neutron star merger with both gravitational waves and electromagnetic light mattered so much. It connected several independent kinds of evidence. The gravitational waves identified the source as a compact binary merger. The kilonova light behaved in ways consistent with neutron-rich ejector and heavy element production. Later comparisons with models showed that such events could contribute substantially to the galaxy's inventory of R-process material. None of this means that every heavy atom has the same origin, or that supernovae have no role at all. The universe often uses more than one channel for a process, but neutron-star collisions provide the kind of neutron richness that the R process demands with unusual force. They are not merely explosions beside dead stars. They are places where the boundary between nuclear matter and chemical matter is crossed in reverse, where a crushed neutron sea is released and allowed to fragment into the elements of ordinary worlds. The pressure inside the R process is thus the pressure of transformation under constraint. Neutrons enter without charge. Nuclei swell beyond stability. Decay changes identity. Fission redirects mass. Expansion freezes the final pattern into matter that can survive. Out of this sequence come elements whose later lives seem entirely different from their origins, silver-shaped by human hands. Iodine moving through biology, uranium warming planetary interiors, gold resting in rock. The process does not make these atoms precious in a human sense. It makes them rare in a cosmic one. because the universe has to arrange collapse, neutron richness, rapid escape, and time in the right order. Once that order is recognized, the question shifts again. The mechanism can build the heavy elements. The harder issue is why the older supernova explanation began to lose its central place, and what evidence forced astrophysics to search for a darker and more compact forge. A core collapse supernova has almost everything that a heavy element forge seems to need. The death of a massive star brings collapse, shock waves, neutrinos, extreme heat, and fresh material already processed through many stages of stellar burning. It throws matter back into the galaxy with enough force to seed future clouds. It also leaves behind the kind of compact remnant where neutrons become abundant and ordinary atomic structure has begun to fail. For much of modern astrophysics, this made supernovae feel like the natural home of the rapid neutron capture process. The story had a satisfying symmetry. Stars make the elements up to the ion group during life, then make the heavier elements in death. The explosion becomes both an ending and a final act of creation. But a satisfying story can be weakened by the details that have to carry it. The question is not whether supernovae are important chemical engines. They scatter oxygen, silicon, sulfur, calcium, iron, nickel, and many other products of stellar evolution. Without them, galaxies would not become chemically rich in the way they do. The narrower question is whether ordinary core collapse supernovae can make and eject enough of the heaviest R-process elements to explain what is actually observed. That question has become harder over time. The first difficulty is abundance. If common supernovae were the dominant source of the heaviest rapid neutron capture material, then their frequency should leave a broad and fairly consistent chemical mark across the galaxy. Massive stars die often compared with neutron star mergers. Their explosions have occurred throughout the Milky Way's history, stirring new material into the interstellar medium again and again. If each one produced large amounts of gold, europium, platinum, uranium, and related heavy nuclei, the cumulative enrichment should be enormous. Yet the patterns seen in old stars and galactic material do not fit so simply. Some ancient stars show strong enhancement in R-process elements, while others with similar iron content do not. This scatter suggests that the source may be rarer, more unevenly distributed, or more specialized than ordinary supernovae. The chemical record does not look like the smooth output of a frequent universal forge. It looks more like a galaxy receiving heavy nuclei from events that are powerful but not common, events whose debris can enrich one region strongly while leaving another comparatively poor. The second difficulty is physical. A supernova is violent, but violence by itself does not guarantee the right conditions. The R process demands a high neutron richness, rapid expansion, suitable temperatures, seed nuclei, and a way for the resulting material to escape. Inside a collapsing massive star, these requirements compete against one another. The shock that launches the explosion must travel through dense layers. Neutrinos stream from the newborn compact remnant and can change the balance between neutrons and protons in the outflow. Matter can be heated, dissociated, reassembled, or pulled back. In some models, the conditions become too proton-rich, meaning there are not enough free neutrons to drive the full R process into the heaviest nuclei. In others, the outflow does not carry enough material with the right composition. The problem is precise rather than dramatic. The explosion can be real, bright, and chemically productive while still failing to produce the full, heavy R process pattern in abundance. A furnace can be powerful without being the correct furnace. Neutrinos are central to this uncertainty. During core collapse, the newborn neutron star releases a vast flood of them. Most pass through matter almost untouched, but in the dense region near the remnant, they influence the nuclear composition of the ejector. They can convert neutrons to protons or protons to neutrons through interactions with nucleons, changing the electron fraction, a measure of how proton-rich or neutron-rich the material is. A small shift in that balance can decide whether an outflow builds light transion elements or reaches the much heavier R process peaks. This makes supernova nucleosynthesis sensitive to details that are difficult to model: completely neutrino energies, flavor changes, turbulence, magnetic fields, rotation, and the shape of the explosion. The more closely the models are examined, the less the old simple picture holds. It is not enough to say that a collapsing star creates neutrons. The environment must keep enough of them available in the right region for the right amount of time and then release the products into space. Some special supernova channels may still contribute. A rapidly rotating massive star with strong magnetic fields could launch jets that carry very neutron-rich material outward. These magnetorotational explosions are not ordinary spherical blasts. They depend on conditions that may be rare, and they could explain some heavy element production, especially in the early galaxy. Other exotic collapses may also play roles. The issue is not whether any supernova anywhere can host an R process. The issue is whether typical supernovae can serve as the main source. As the evidence accumulated, that broad claim became less secure. Supernovae remained essential to cosmic chemistry, but their role in making the heaviest R process elements narrowed. They were no longer the simple answer that could carry the entire burden of gold. Observations added pressure from another direction. The nearest well-studied supernova of modern astronomy, seen in the Large Magellanic Cloud in the late 20th century, gave scientists an extraordinary chance to examine the aftermath of a core collapse event relatively close by cosmic standards. It confirmed many aspects of massive star death and radioactive production, but it did not reveal the kind of strong R process enrichment that would have strengthened the older view. One object cannot settle the question alone, because supernovae differ in mass, structure, rotation, magnetic field, and environment. Still, the absence mattered. It reminded researchers that a spectacular explosion is not automatically a heavy R process factory. What can be made in theory must also appear in the debris that nature actually releases. The chemical fingerprints have to be present, not merely plausible. Meanwhile, the oldest stars in the Milky Way carried their own testimony. Some stars formed early, when the galaxy had been enriched by only a limited number of previous events. Their atmospheres preserved the composition of the gas from which they formed. In certain metal-poor stars, R process elements appear in patterns that closely resemble the solar system's heavy R process distribution, even when the total amount varies strongly. That combination is revealing. The process that made those elements seems capable of producing a robust pattern once it happens, but it did not happen everywhere at the same level. A rare event with high yield fits that picture better than a frequent event with small, uniform yield. This does not remove every uncertainty, because early galactic mixing is complex and different sources can overlap, but it shifts the weight of interpretation. The source of the heaviest elements begins to look less like the ordinary death of many massive stars and more like a smaller number of extreme events, whose debris leaves deep local marks. Neutron star mergers answer several of these pressures at once. They are rare compared with supernovae, but they can eject matter that is naturally neutron-rich. Their debris is not merely close to the right conditions, it begins with material born from the crushed interior and crust of neutron stars themselves. A single merger can produce a large amount of R process material, enough to influence the chemical evolution of a region despite the event's rarity. This high-yield, low-frequency pattern helps explain why R process enrichment can be patchy in old stellar populations. It also gives a physical reason for why the heaviest nuclei can be made efficiently. The source does not have to manufacture neutron richness as a delicate byproduct of a complicated explosion. It releases neutron-rich matter directly from compact stellar remnants. The rise of neutron star mergers as the leading candidate was therefore not a sudden rejection of supernovae as cosmic creators. It was a refinement of what different deaths can do. Massive stars still build much of the periodic table up to the iron group and distribute it through explosive collapse. Some may make certain heavy elements under unusual conditions, but the strongest case for the main origin of gold and many related nuclei moved toward collisions between neutron stars because the evidence demanded a source that was rarer, richer in neutrons, and able to eject a large mass of R-process debris. The old narrative of supernovae making everything beyond iron had been elegant. The newer narrative is less simple, but it is more closely fitted to the data. It divides cosmic creation into more specialized events, each with its own limits and signatures. The doubt around supernovae does not weaken the story of heavy elements. It clarifies it. It shows that the universe does not rely on one kind of stellar catastrophe to do all chemical work. Some deaths scatter the products of burning, some collapse into remnants that wait in silence, and some remnants, paired by gravity and slowly drained by waves in space-time, carry the unfinished chemistry of the heaviest elements toward a later collision. Once supernovae cease to be the whole answer, the path narrows toward binary dead stars, where the source of the neutron flood is not a passing condition inside an explosion but the substance of the stars themselves. A binary neutron star system begins as an aftermath rather than a beginning. Before there are two compact remnants circling each other in the dark, there were once two massive stars bound in a common gravitational story, born from the same cloud or captured into the same long companionship. Each star lived quickly by stellar standards, spending its fuel under tremendous internal pressure, building heavier elements in its core, shedding winds, swelling, stripping material from its companion, and finally collapsing when its central support failed. The first supernova could have torn the pair apart, the second could have done the same. In many cases, such systems do not survive. Explosions are asymmetric. Mass is lost suddenly, and the newborn remnant may be kicked away by the uneven violence of collapse. For a future neutron star merger to exist, the binary has to pass through this dangerous sequence without being separated. It is a rare survival of stellar death. A pair of corpses remaining gravitationally bound after both original stars have vanished as ordinary suns. The calmness of the orbit after that history is deceptive. Nothing about the system is truly still. Each neutron star may contain more mass than the Sun inside a sphere only about the width of a large city. Their surfaces are not surfaces in the familiar planetary sense, but crusts of dense nuclear matter over interiors where pressure and gravity have remade the ordinary behavior of atoms. Around them, space-time is strongly curved. Between them, gravity holds the pair in a mutual fall that never quite completes, because sideways motion continually carries each star around the other. From a distance, this can look stable. The stars circle again and again, perhaps for millions or billions of years, with no flame, no expanding shell, and no visible warning that a collision waits inside the mathematics of the orbit. Yet general relativity gives such a binary a quiet leak. Accelerating masses in a strong gravitational field emit gravitational waves, ripples in space-time that travel outward at the speed of light. These waves carry energy away from the orbit. The loss is usually tiny, but a neutron star pair is compact enough and massive enough for the effect to accumulate. Each orbit is a little smaller than the one before it. Each revolution happens a little faster. The binary is not merely circling, it is inspiraling. The word captures the essential motion, because the path is a spiral inward, driven not by friction against gas or dust, but by the radiation of gravity itself. No ordinary wind slows the stars. Space is not dragging them like water. Instead, the shape of space-time is changing. An energy that once belonged to orbital motion departs as waves that spread through the universe. For most of the binary's life, this decay can be extremely gradual. The system may spend vast ages with a separation large enough that the final collision remains remote. During that time, it can drift through the galaxy far from the stellar nursery where its first stars formed. Supernova kicks may send it into the outskirts of a galaxy or into a region with little gas, making its later collision appear displaced from the bright places where massive stars are being born. This displacement matters when interpreting heavy elements. If neutron star mergers are rare and can occur long after their progenitor stars die, their enrichment may enter the galaxy in scattered and uneven ways. The debris from one event does not mix instantly into every cloud. It spreads, cools, joins interstellar currents, and becomes part of later generations of star formation only after complex motion. A binary dead star system is therefore not only a compact object problem, it is also a chemical delivery system with a delayed fuse. The fuse is gravity, and it burns by emitting waves too subtle for human instruments to have detected until very recently. The first strong evidence that such orbital decay was real came from a binary pulsar, a system in which at least one neutron star sent out regular radio pulses like a lighthouse made by rotation and magnetic fields. Its pulses allowed astronomers to time the orbit with extraordinary precision. Over years, the orbit shrank exactly as general relativity predicted from gravitational wave emission. Long before detectors directly felt the waves from merging black holes and neutron stars, this timing acted as an indirect witness. It showed that compact binaries do not merely obey Newtonian orbits forever. They radiate their motion away. The final merger is not an added catastrophe imposed from outside. It is the natural endpoint of a process already written into the orbit. As the stars draw closer, the leakage accelerates. Gravitational wave power rises sharply as separation decreases. The orbit quickens from a slow celestial clock into an increasingly rapid whirl. Near the end, the stars can circle each other many times in a single second, their mutual gravity stretching and deforming their outer layers. Tidal forces become stronger. The crusts, already under extreme stress, approach conditions that can crack, heat, or rearrange matter. Magnetic fields may twist and reconnect. The boundary between two separate bodies begins to lose its clean simplicity before actual contact. In the last stages, the binary is a coupled system of gravity, nuclear matter, magnetism, and radiation, each part feeding back into the others. The precise behavior depends on the masses of the stars and on the equation of state of neutron star matter, a term for how such matter responds to pressure at densities beyond atomic nuclei. This uncertainty is one reason neutron star mergers are scientifically valuable. They are not only factories for heavy elements, they are experiments in matter under conditions unreachable on Earth. The orbit can also reveal what the stars are made of. Perfectly rigid point masses would spiral inward in one way. Real neutron stars are not points. They can be tidally deformed by each other's gravity, and that deformation slightly changes the gravitational wave signal. The amount of deformation depends on the internal stiffness of the stars. If neutron star matter is relatively stiff, the stars are larger and more easily distorted. If it is softer, they are more compact and resist deformation differently. Thus the waveform carries information from deep inside matter that no telescope can image directly. The chirp of the final inspiral is a coded message about mass, radius, gravity, and nuclear physics. It is also the warning that a chemical event is approaching, because the same deformation that leaves traces in space-time will soon help tear neutron-rich material into the open. There is a quiet contradiction in such binaries. They are among the densest objects that can exist without becoming black holes, yet for most of their history they may be almost invisible, unless one is seen as a pulsar, or unless surrounding material happens to reveal them. They can move through the galaxy unnoticed. Their future violence does not announce itself in ordinary light. It is stored in the shrinking orbit. This hiddenness helps explain why their role in heavy element production was difficult to confirm for so long. A supernova declares itself with light. A neutron star binary, before merger, can look like nothing at all. Its most important output is not a glow, but a gradual export of orbital energy into space-time. Only in the final moments does the system become loud in the new astronomy of gravitational waves, and only after collision does it become chemically visible through kilonova light. The birth of gold is therefore preceded by a long darkness. The dead stars must first wait through an age of orbital narrowing, keeping their neutron-rich interiors sealed away while gravitational radiation draws them closer. By the time the final approach begins, the system has already passed through several thresholds. It survived 2 stellar deaths. It remained bound after explosive mass loss. It aged through a long in-spiral. It carried its compact matter across space until separation fell low enough for gravitational waves to drain energy with overwhelming speed. These thresholds make the merger rare, but they also make it efficient. When the collision finally comes, the stars do not need to invent neutron richness. They arrive made of it. Their substance has been prepared by collapse, preserved by pressure, and delivered by orbital decay to the moment when it can be released. That is why binary dead stars occupy such a central place in the modern story of heavy elements. They are not simply 2 remnants falling together. They are delayed consequences of massive stellar evolution, compact reservoirs of neutrons, gravitational wave sources, and future kilonova engines all at once. Their quiet in spiral is the long prelude to a much shorter act of creation. The next movement begins when the orbit can no longer be treated as a slow decay, when each revolution tightens so rapidly that the stars pass from companionship into contact, and the hidden matter of their interiors begins to enter open space. The final milliseconds of a neutron star merger are not simply a faster version of the long in spiral. They are a different physical state, where the clean idea of 2 separate stars begins to fail. Until this point, the binary can still be described as 2 compact bodies losing orbital energy to gravitational waves. Their masses curve space-time, their motion produces a rising signal, and their separation shrinks according to the rules of relativity. But as the surfaces draw close, the stars begin to feel each other not as distant companions, but as tidal forces across their own bodies. Gravity no longer pulls each star as a whole in one simple way. The near side feels a stronger pull than the far side. Matter stretches. The crusts deform. The outer layers, already held in a state unlike any ordinary solid, begin to respond to a force that changes from moment to moment. The orbit accelerates so quickly that each passage is not quite like the previous one. The stars are still recognizable, but their individuality is ending. In this narrow interval, the collision begins before the surfaces fully touch. Tidal arms can draw neutron-rich material outward, forming curved streams that trail around the system. Some matter is flung into escape paths directly, thrown loose by the gravitational slingshot of the merger. Other material remains bound, wrapping into a hot, dense torus around the central remnant. This distinction matters because only the matter that escapes can enrich the galaxy. Material that stays too close may later fall inward and vanish behind an event horizon if a black hole forms. The merger is therefore also a sorting process. Some of the neutron-rich substance is released into the future of interstellar chemistry, while some is lost to the compact remnant that the collision creates. The birth of heavy elements depends not only on the violence of impact, but on the geometry of escape. The gravitational wave signal reaches its highest urgency in this same moment. During the inspiral, the waves rise in frequency and strength, producing a chirp whose shape reveals the masses and orbital motion of the stars. Near contact, that signal carries subtler information about the way the stars deform. If matter inside them is stiff, their tidal bulges differ from what softer matter would produce. The waveform is altered by the internal physics of nuclear density. Then, as the stars merge, the clean chirp ends. What follows depends on the total mass and the nature of the equation of state. Sometimes the merged object may collapse almost immediately into a black hole. Sometimes it may form a hypermassive neutron star, an unstable remnant temporarily supported by rapid rotation and heat. That survival may last only a fraction of a second, or longer, before collapse. In either case, the central object is surrounded by debris whose future determines much of the observable light. The word collision can mislead if it suggests two hard spheres striking and bouncing. Neutron stars do not meet like stones. Their matter is fluid in the deeper sense, governed by gravity, nuclear forces, pressure, magnetic fields, and relativistic motion. When contact occurs, the boundary between them shears and folds. Shock waves pass through dense material. Temperatures rise to levels where atomic nuclei can be broken apart and reassembled. Neutrinos pour out from the hot remnant and surrounding disk. Magnetic fields may be twisted and amplified by turbulence, perhaps shaping outflows or helping drive jets. The merger is not a single impact, but a short-lived engine that rearranges matter through several overlapping channels. Tidal ejector, shock-heated ejector, disk winds, neutrino-driven flows, and magnetically influenced outflows can all carry different compositions into space. Each channel has its own neutron richness, speed, and contribution to the final element pattern. This is why the last milliseconds are scientifically dense. In that brief time, the system decides how much matter will be thrown out, how neutron-rich it will be, how fast it will expand, and whether it will be accompanied by a jet energetic enough to produce a short gamma-ray burst. A slight difference in mass ratio may change the amount of tidal stripping. A slight difference in total mass may change how quickly the remnant collapses. A longer-lived remnant can bathe the surrounding debris in neutrinos for a longer time, raising the number of protons in some outflows and altering which elements form. A prompt black hole collapse may trap more material and leave a different chemical signature. The same basic event, two neutron stars merging, can therefore produce varied outcomes. The category is unified, but the details are not interchangeable. The first material to escape is often among the most neutron-rich, torn from the outer regions and flung out dynamically. It can begin rapid neutron capture almost as soon as pressure drops and expansion begins. The matter is released from the conditions that kept it in nuclear balance inside the star. It is suddenly in open space, still dense enough for reactions but no longer stabilized by the same crushing gravity. Free neutrons are abundant. Seed nuclei form or survive. The R process begins in a rush. In some parts of the outflow, nuclei can be driven toward the heaviest elements, even into regions where fission cycles may occur and reshape the final abundances. In other parts, where neutrino exposure has made the material less neutron-rich, the process may favor lighter heavy elements. The merger does not produce one uniform chemical soup. It produces layered, directional debris, with composition tied to the path by which each piece escaped. Around the remnant, the accretion disk becomes another site of transformation. This disk is not a calm ring like the imagined edge of a planetary system. It is hot, dense, turbulent, and temporary. Matter orbits at extreme speed, heated by friction, shocks, and magnetic stresses. Some of it spirals inward and feeds the central compact object. Some is driven outward in winds. These disk winds can carry additional R-process material, sometimes with a different neutron richness than the earliest tidal ejector. They may contribute significantly to the total mass of heavy elements released. If a black hole is already formed, the disk orbits just outside an event horizon, and the question becomes how much matter can be expelled before gravity consumes it. If a massive neutron star remnant survives briefly, its neutrino radiation and magnetic field can alter the disk outflows before collapse. In both cases, the new elements are born near a threshold where matter either escapes into the galaxy or disappears from observable history. The formation of a black hole, when it happens, gives the event a sharper edge. The merged mass may exceed what neutron degeneracy pressure and nuclear forces can support. Rotation and heat can delay collapse, but they cannot always prevent it. When the remnant falls inward beyond the event horizon, the densest central matter is cut off from the outside universe. The black hole does not announce its interior. It leaves only its gravity, its surrounding disk, and the consequences of what escaped before or during collapse. This makes the merger almost paradoxical as a forge. It creates heavy elements next to a region from which nothing can return. Gold and uranium may form in debris orbiting or fleeing the rim of a newborn black hole, while nearby matter crosses into permanent silence. Creation and disappearance occur almost side by side. The chaos is not disorder without structure. It is governed by laws that can be read in several messengers. Gravitational waves report the motion of the masses and the deformation of the stars, gamma rays. If a jet is launched and pointed favourably, reveal a narrow channel of relativistic energy. The kilonova glow records the radioactive heating of expanding R-process material. Later spectra and fading colours hint at the opacity of heavy elements in the debris. No single messenger tells the whole story. Together, they turn the final milliseconds from an invisible calculation into an observed sequence. They show that the collision is not merely an end state for two compact remnants. It is a moment when space-time, nuclear matter, radiation, and chemistry become inseparable. By the time the stars have fully merged, the heavy element story has already passed through its most decisive gate. Some matter has been torn loose, some has been shocked into outflow, some has entered a disk that may later breathe heavy nuclei into space, some has fallen inward and will never be part of a planet. The final milliseconds do not merely destroy the binary. They divide its substance into memory and disappearance, into material that the galaxy can inherit and material that is removed behind gravity's boundary. What follows is light the expanding, fading, colour-changing signal of a kilonova, where the invisible nuclear work of these moments becomes visible across intergalactic distance. The first light after a neutron star collision does not behave like the light of an ordinary supernova. It rises from a smaller amount of matter, expelled at enormous speed, carrying a composition that changes how radiation moves through it. The debris is not only hot gas expanding into space, it is new chemistry in motion, filled with unstable nuclei whose decay releases heat as the cloud spreads outward. This glow is called a kilonova, a name that places it between familiar stellar explosions in brightness, but does not fully capture its importance. A kilonova is not simply a flash from impact. It is the visible surface of rapid neutron capture cooling into the periodic table. It begins after the gravitational wave chirp has ended, when the compact bodies have already merged and the immediate violence has passed into expansion. What remains outside the central remnant races away, carrying the products of tidal tearing, shock heating, disk winds, and radioactive transformation. The event becomes observable not because individual nuclei can be watched as they form, but because their collective presence changes the colour, timing, and fading of the light. At first, the outflow can be hot enough to shine in bluer wavelengths, especially if some of the ejecta contains lighter R process elements and has been altered by neutrino exposure. This material may contain fewer lanthanides, a group of heavy elements whose complicated electron structures make them especially effective at absorbing visible light. When lanthanides are scarce, photons escape more easily, and the early glow can be brighter and bluer. But the merger ejecta is not uniform. Other parts of the debris remain more neutron-rich and build heavier nuclei, including lanthanides and perhaps actinides. These atoms create high opacity, meaning they make the material more difficult for light to pass through. Radiation is absorbed and re-emitted many times before it escapes. The result is a redder, longer-lasting component of the kilonova, a deeper glow that emerges as the ejecta expands and cools. Colour therefore becomes evidence. The shift from blue toward red is not only an aesthetic change in a fading point of light, it is a sign that the outflow contains different layers of matter, with different neutron histories and different heavy element yields. The heat source inside the expanding cloud is radioactive decay. Fresh R-process nuclei are born unstable, far from the stable arrangements that later persist in planets and rocks. As they decay, they release energy into the surrounding material. That energy keeps the ejecta shining after the initial collision. The light is therefore delayed information from nuclear instability. It carries the signature of matter settling down from extreme neutron richness toward more durable forms. In a supernova, radioactive nickel and cobalt can help power the light curve, and the expanding star's outer layers create a broad, luminous display. In a kilonova, the radioactive inventory is more varied and heavier. Many nuclei contribute, each decaying on its own timescale, together producing a glow that changes quickly compared with most supernovae. The event can brighten and fade over days rather than lingering with the same profile for much longer. Its speed is part of its identity. The ejecta mass is smaller, the expansion velocity is high, and the opacity depends strongly on which elements have formed. The light curve becomes a coded record of mass, velocity, composition, and radioactive heating. When the first well-observed neutron-star merger was detected through gravitational waves and then followed by telescopes, the kilonova that appeared gave the R-process story a new kind of anchor. The gravitational waves identified the collision. The brief gamma-ray signal suggested a relativistic outflow. The optical and infrared light then evolved in a way that matched expectations for expanding neutron-rich debris. It began relatively bright and blue, then dimmed and reddened as heavier material shaped the escaping radiation. This combination mattered because each messenger removed a different ambiguity. A strange optical transient alone could be argued over. A gravitational wave signal alone could reveal the compact merger but not the chemical aftermath. Together, they showed a physical sequence. Two neutron stars spiraled together, collided, ejected material, and produced light consistent with heavy element creation. The universe had supplied not just a theory of gold, but an observed event where the theory had to face the sky. Spectra deepened the interpretation, though not in a simple way. In astronomy, a spectrum divides light by wavelength, allowing atoms and ions to leave patterns of absorption and emission. For many familiar elements, these patterns can identify composition with great precision. Kilonova spectra are harder. Heavy R-process elements have many possible electron transitions, and the ejecta moves so quickly that spectral features are broadened and blended. Instead of neat fingerprints, Observers often find wide shapes and changing colours that must be compared with complex models. This makes the evidence powerful but cautious. The kilonova does not display a clean label saying gold was made here. It shows a pattern of brightness, colour, opacity, and fading that points toward neutron-rich heavy elements in bulk. Some individual species may be suggested under favourable conditions, but the larger conclusion comes from the whole behaviour of the transient. The data does not remove uncertainty by becoming simple. It becomes persuasive because several difficult pieces align. The red component is especially important for the heaviest elements. Lanthanides, with their dense forests of electron transitions, can trap visible photons and push the escaping light toward infrared wavelengths. A kilonova rich in such material will not look like a clean blue fireball for long. It becomes dimmer to ordinary optical sight and more visible in red and infrared light. In that sense, the heavy elements hide themselves even as they announce their presence. They make the glow harder to see in some wavelengths precisely because they are there. This is one of the subtle reversals of the event. The stronger the production of certain heavy nuclei, the more the ejector can cloak its own radiation. Observers must follow the fading source quickly, across multiple wavelengths, before the signal sinks beyond reach. A kilonova is not a patient object. It is a brief chemical flare, and the evidence it offers is strongest when captured early and continuously. The expansion also gives the event its shape in time. Matter thrown out at a significant fraction of the speed of light rapidly becomes more diffuse. At the beginning, photons are trapped by density and opacity. As the debris spreads, the path to escape becomes easier. Light emerging at any moment has been filtered by the expanding material around it. The observed brightness rises when heating, diffusion, and expansion reach a balance, then fades as the radioactive power drops and the cloud thins. Different ejector components peak at different times. Faster, less opaque material can shine earlier. Slower, lanthanide-rich material may peak later and redder. The kilonova is therefore not one glow, but a layered release of information. It is the collision's debris becoming transparent in stages. Each stage exposes a different part of the outflow's composition and history. Beneath this light lies the question of quantity. A single neutron star merger can eject enough R-process matter to influence galactic chemical evolution, but the exact amount varies. Models infer totals from light curves, velocities, and opacity. While gravitational waves constrain the masses of the merging stars, the estimated yield from the observed event was large enough to make neutron star mergers serious contributors to the cosmic supply of heavy elements. This did not mean that one event explained every atom of gold in the universe. It meant that the mechanism had passed a crucial test. It could occur in nature, eject neutron-rich material, and produce a kilonova consistent with heavy element formation. After decades of uncertainty around supernovae, that was a major shift. The question changed from whether neutron star mergers could do the work at all to how often they occur, how much they eject, how their yields vary, and how their debris mixes into galaxies over time. The fire of a kilonova is brief, but its consequences are not. The atoms formed in that expanding cloud may outlive the stars that made them. Once the debris cools enough, it joins the interstellar medium, where it can be diluted, swept into clouds, incorporated into new stars or locked into planets. The light fades in days. The nuclei can remain for billions of years. Some are stable, some decay over long spans, heating matter or transforming into daughter elements. The mismatch between the short glow and the long material afterlife is one of the event's quietest meanings. A kilonova is the visible announcement of a chemical inheritance that will soon become invisible, spread too thinly across space to be recognized as the one event, until future minerals or stellar atmospheres preserve its trace. By the time the red light fades, the story has already moved away from spectacle. The merger has become expanding matter, and expanding matter has begun its long passage toward incorporation. This is why the kilonova is more than an afterglow. It is the bridge between gravitational catastrophe and ordinary substance. Gravitational waves reveal the final dance of compact remnants. Nuclear physics explains how neutron-rich ejecta can assemble heavy nuclei. The kilonova shows that some of those nuclei escaped, heated their surroundings through decay, and changed the colour of the light as they moved outward. It gives the birth of gold a visible weather first hot and open, then redder, slower, more obscured by the very elements being made. The glow closes the instant of collision and opens the longer problem of survival. Matter has been created, but it must still avoid falling back, pass through radiation, expand into the galaxy, and become part of the clouds from which later systems form. The next question is how such heavy nuclei, born so close to collapse, manage to ride outward at all, leaving behind the gravity of the remnant and entering the wider chemical memory of space. Neutrinos are usually introduced as particles that almost never stop. They pass through planets, stars, and bodies of rock with only the faintest chance of touching anything on the way. In ordinary matter, this ghostly behaviour makes them seem like weak messengers, useful because they escape from places light cannot, but too elusive to push very much around. Near a neutron-star merger, that familiar picture has to be adjusted. The particles themselves have not changed their nature. They still interact through the weak nuclear force. What changes is the environment. The density of matter is extreme, the temperature is enormous, and the number of neutrinos released by the hot remnant and surrounding disk becomes so large that even rare interactions begin to matter. In the first moments after collision, a wind made partly by neutrino heating can help decide whether newly formed heavy nuclei remain trapped near the compact remnant or enter the wider galaxy. The effect is delicate, but its consequence is large. It turns particles known for passing through everything into one of the possible escape routes for matter, born beside gravity's deepest thresholds. The source of this neutrino flood lies in the violence of nuclear transformation. When neutron-rich matter is torn from the stars and decompressed, it does not remain in the same state it held under crushing pressure. Free neutrons and neutron-heavy nuclei begin to move away from stability. Beta decay becomes common. In beta decay, a neutron changes into a proton while releasing an electron and an antineutrino. In the hottest inner regions, related reactions involving electrons, positrons, protons, and neutrons also produce neutrinos and antineutrinos in vast numbers. The central remnant, whether it is a massive neutron star surviving briefly or a newly formed black hole with a dense disk around it, becomes surrounded by a field of escaping neutrinos. Most of them stream away and carry energy with them. Some are absorbed by nearby matter, some change neutrons into protons or protons into neutrons through weak interactions. These small nuclear adjustments can alter the electron fraction of the outflow, the balance that determines how neutron-rich the material remains. That balance matters because it shapes both chemistry and escape. If matter stays extremely neutron-rich, it can drive the rapid neutron capture process toward very heavy nuclei, including lanthanides and actinides. If neutrino interactions raise the proton content, the same outflow may favour lighter heavy elements. The wind, therefore, does not simply move matter. It edits its composition while it moves. Around the merger remnant, gravity is trying to keep almost everything. Matter in the accretion disk orbits at immense speed, heated by shocks, turbulence, and magnetic stress. Some of it spirals inward. Some of it is lifted outward by pressure, magnetic fields, viscous heating, nuclear recombination, and neutrino absorption. These mechanisms overlap, compete, and strengthen one another in ways that depend on the lifetime of the remnant. If a black hole forms almost immediately, the disk still shines in neutrinos. But the central source is different from a longer-lived neutron star remnant. If the merged object survives for a brief interval as a hot massive neutron star, its surface and surrounding material radiate neutrinos intensely, bathing the disk and polar regions in energy. That radiation can heat matter enough for some of it to rise out of the potential well. Escape, in this setting, is not a single leap. It is the gradual acquisition of enough energy, in the right direction, before the remnant's gravity draws the material inward again. The phrase neutrino wind can make the process sound smoother than it is. There is no gentle breeze in the familiar sense. There is a flux of nearly weightless particles, moving outward from an environment where nuclear matter has been shredded and reorganized. When a neutrino or antineutrino is absorbed by a neutron or proton, it can deposit energy and change the particle's identity. Each interaction is small, but the scale of the flux makes the cumulative effect meaningful. Matter near the remnant can be heated, lifted, and altered. In some regions, especially above the poles of a surviving neutron star remnant, this heating may help produce a relatively proton-rich outflow. In other regions, colder tidal debris remains much more neutron-rich and less affected by neutrinos. The merger is therefore chemically directional. The same event can send one stream outward with conditions suited for the heaviest rapid neutron capture elements, while another carries lighter products formed under stronger neutrino influence. Beta decay adds another layer to this escape story because it is both a maker of elements and a source of energy. As neutron-rich nuclei decay, they release particles and heat. This decay energy helps power the kilonova, but it also reflects the fact that the outflow is internally changing as it expands. The nuclei are not finished at the moment they are ejected. They continue to settle towards stability during flight. Each decay can shift the atomic number, turning one element into another. The final abundance pattern is therefore frozen in only gradually, as neutron captures cease. Beta decays proceed, and some very heavy nuclei fission into smaller fragments. The material leaving the merger is less like finished ore than a cloud of nuclear possibility, cooling into definition as it moves. By the time it becomes part of interstellar dust, the brief physics of the remnant has become stable chemistry. The path out of the merger also depends on timing. Material launched immediately by tides may escape before neutrino irradiation changes it much. Shocked matter near the collision interface may be hotter and more exposed. Disk winds can continue for longer, emerging after the initial dynamical ejector has already fled. If the central remnant survives longer, neutrino exposure may continue longer, changing the composition of later outflows. If collapse happens quickly, some potential wind material may be swallowed before it can leave, and the balance shifts toward the matter thrown out earlier. This is why the lifetime of the post-merger remnant matters so strongly. It determines not only the gravitational outcome, but the chemical one. A difference of milliseconds can change the quantity and character of matter available for the galaxy. Magnetic fields and rotation can also shape the outflow, adding energy to disk winds and helping matter leave over longer timescales than the first impact. The details remain difficult because they involve general relativity, nuclear physics, neutrino transport, magnetic fields, and matter at nuclear density. Still, the broad picture gives the escape its true complexity. The newly made elements are not simply blasted outward by an explosion and left alone. They are selected by their trajectory, transformed by weak interactions, heated by radioactive decay, and carried by winds whose power comes from several physical sources at once. Their survival is a negotiated outcome between expansion and capture. This negotiation gives the merger its strange intimacy with black holes. If the central remnant collapses, the event horizon becomes a boundary beyond which no newly made atom can later return. Yet just outside that boundary, the disk and outflows may still be rich with material that has crossed the iron limit and climbed into the heavy end of the periodic table. The difference between an atom that becomes part of cosmic inheritance and a particle lost behind the horizon may be a matter of path and timing. One parcel of matter gains enough energy from tidal motion, disk turbulence, nuclear recombination, magnetic stress, or neutrino heating, then moves outward as part of the kilonova ejector. Another parcel spirals inward and vanishes from the observable universe. Both began in the same merger. Only one becomes available to the future. Neutrinos are therefore not a decorative detail in the story. They help connect the hidden nuclear interior of the event to the visible and chemical aftermath. They carry energy from dense regions that photons cannot easily leave. They modify the neutron richness that determines which elements form. They may help lift matter into outflow, especially where the remnant radiates most intensely, and because they interact only rarely, they also show the limits of influence. A neutrino wind can assist escape, but it does not rescue everything. Much of the matter remains bound. Some is swallowed, some never becomes part of the expanding debris. The heavy elements that do escape are the successful fraction of a harsher sorting. Their later calm depends on a moment when they found a path outward through radiation, gravity, and decay. Once this path is understood, the birth of gold no longer looks like a single flash. It looks like a sequence of narrow permissions. Matter must be torn loose from neutron stars. Nuclei must capture neutrons faster than they decay. The remnant must eject some of the debris before collapse or fallback claims it. Neutrino flows and beta decay must shape the composition without erasing the neutron richness completely. The expanding material must remain intact long enough to cool, shine, and disperse. Only then can the products of the merger enter the interstellar medium, where they become available to a later solar system. The escape is not the end of the journey. It is the moment when the new elements stop belonging only to the catastrophe and begin belonging to the galaxy. The next evidence for that journey is not found in the fading light of a distant kilonova, but in the old solids of the early solar system, where radioactive clocks preserve the timing of a collision that occurred before Earth had formed. Ancient meteorites preserve a kind of evidence that no telescope can collect from the present sky. They are not bright. They do not carry an image of the event that enriched the young solar system. Their value comes from being old enough to have formed when the sun and planets were still assembling from a shared cloud of gas and dust. In those early solids, minerals locked in chemical ratios before Earth existed as a finished world. Later, melting, weathering, plate motion, and biological cycling altered much of the planet's original record. But certain meteorites remained comparatively unchanged, small archives from the beginning of the solar system. Inside them, scientists can read the traces of radioactive atoms that have long since vanished. The atoms themselves are gone, changed by decay into daughter elements, yet their absence is not empty. It leaves proportions, excesses, and deficits. It leaves a clock built from what is no longer there. This is how the story of neutron star collisions moves from gravitational waves and kilonova light into stone. The same heavy element creation that once unfolded beside collapsing remnants can be measured through minerals that cooled in the first solid material around the young sun. The principle is quiet and powerful. A radioactive isotope is unstable, and over time it changes into another isotope or element at a predictable average rate. The half-life describes how long it takes for half of a population of such nuclei to decay. If the parent isotope survives, its abundance can be compared directly with its decay products. But many of the isotopes that matter for early solar system history had half-lives far shorter than the age of Earth. They disappeared billions of years ago. Their usefulness remains because some daughter products stayed trapped in the same mineral systems where the parents once existed. When a mineral formed, it incorporated certain atoms and excluded others according to chemistry. If a short-lived parent isotope was present at that moment, its later decay added daughter atoms inside the mineral. By comparing the daughter excess with stable reference isotopes, scientists can reconstruct how much of the parent was present when the solid formed. The parent has vanished, but the daughter remembers it. For our process material, this becomes especially revealing. Heavy nuclei made in neutron star mergers are not all equally stable. Some remain nearly unchanged over the age of the solar system. Others decay on timescales of millions or tens of millions of years. These short-lived species are difficult witnesses because none remain today. Yet they are also more precise clocks. A long-lived isotope can say that material was made sometime in a broad past. A short-lived isotope fades quickly enough that its remaining signature depends strongly on the interval between its creation and its incorporation into early solar system solids. If two radioactive isotopes are produced together and one decays faster than the other, their ratio changes with time. The ratio locked into meteorite material therefore carries information about the delay between the nucleosynthetic event and the formation of the solids. It is not a direct photograph of a merger. It is a timed chemical shadow. One important comparison involves curium-247 and plutonium-244, two heavy radioactive isotopes associated with rapid neutron capture. Curium-247 decays more quickly. With a half-life of about 15.6 million years, plutonium-244 lasts longer, with a half-life of about 80 million years. If both were produced in the same neutron-rich event, their relative abundance would begin at a value set by nuclear physics and the conditions of the source. After that, the curium would diminish more rapidly than the plutonium. By the time early solar system minerals formed, the ratio between them would reveal how much time had passed. Because neither parent isotope remains in ordinary early solar system material today, the measurement relies on daughter products preserved in meteorites. The logic is subtle, but the meaning is direct. A mineral grain can contain the afterimage of atoms made before the sun existed, and the difference between two vanished clocks can narrow the timing of the event that supplied them. The results suggested that at least some short-lived R-process material in the solar system did not come from a smooth background of many well-mixed events. It may have come from a single nearby neutron star merger that occurred before the sun formed. Close enough to seed the cloud that became the solar system, and recent enough that short-lived isotopes had not all decayed away. The estimated timing falls within a span of tens to a little over 100 million years before solar system formation, and the distance may have been on the order of hundreds to somewhat more than 1,000 light-years. These numbers are not the kind of precision found in a laboratory clock on a table. They depend on models of isotope production, galactic mixing, dust transport, and the uncertain behavior of neutron star merger ejecta. But the conclusion is still striking. A rare collision between dead stars, occurring in the solar neighborhood before there was an Earth, may have left chemical signatures that later became trapped in the oldest rocks available for study. This is where rarity becomes useful. If neutron star mergers happened as often as ordinary supernova, the early solar system might have inherited a smoother blend of many events, making a single source harder to identify. But because mergers are uncommon and can produce large amounts of R-process material at once, a nearby event can stand out in the record of short-lived isotopes. The galaxy does not mix instantly. Material ejected from a merger has to travel through interstellar space, slow, cool, condense into dust or join gas, and become incorporated into a star-forming region. The meteorite record preserves only the fraction that entered the molecular cloud or disk from which the Sun formed. This makes the evidence both powerful and incomplete. It can reveal that certain atoms were present at the beginning, and it can constrain when they were made, but it cannot show the full journey of each nucleus from merger debris to mineral lattice. The early solar system itself was not a quiet container. It was a disk of gas and dust rotating around the young Sun, with particles colliding, melting, evaporating, and condensing. The first solids formed under high temperatures close to the young star, while other materials accumulated farther out in colder regions. Small bodies grew, broke apart, and reassembled. Some became parent asteroids of meteorites. In that active environment, isotope signatures had to survive heating and chemical separation. The fact that useful records remain at all is remarkable. They are patterns extracted through careful measurement, comparing one isotope system with another and asking which history fits all the constraints. The ancient meteorite does not tell its story in a single line. It offers a set of ratios, and the interpretation comes from placing those ratios inside a larger model of nuclear decay, early solar chemistry, and galactic enrichment. There is a deep contrast between the size of the event and the scale of the evidence. A neutron star merger can release gravitational waves across the universe and throw out enough heavy material to weigh many Earths. A meteorite sample may be held in a laboratory instrument, its story carried by atoms too sparse to see even under magnification. Yet the small record can reach back to the large event, because radioactive decay is indifferent to scale. A nucleus does not know whether it belongs to a cloud, a planetesimal, or a laboratory sample. It decays according to its own probability, leaving a daughter product that can later be counted. The enormous collision and the quiet mineral are linked by the same nuclear law. It uses the remaining order inside matter to infer the timing of events that no human observer could have seen. Still, caution remains part of the story. The production ratios of curium, plutonium, and other heavy isotopes depend on the exact conditions in the R-process source. Different neutron star mergers may not produce identical patterns. Some supernova-related channels or other rare events might contribute to certain isotopes. The interstellar medium is not a perfectly mixed reservoir. Dust grains can preserve local anomalies, and early solar system processing can complicate the record. The strength of the meteorite clock comes not from removing all ambiguity, but from narrowing what is plausible. It shows that the solar system began with a particular inventory of short-lived radioactive nuclei, and that some of those nuclei are most naturally explained by a recent nearby source of rapid neutron capture material. The collision itself is gone, its light long faded, its gravitational waves long past. What remains is the arithmetic of decay inside stones older than Earth. Meteorite clocks turn the birth of gold from a distant cosmic event into a dated inheritance. They suggest that the heavy elements of the young solar system were not all ancient background dust, mixed beyond recognition from the whole history of the Milky Way. Some were fresher, some had arrived not long before the Sun formed, carrying the imprint of a compact merger into the raw material of planets. The evidence is small, but it reaches into a precise kind of darkness the time before Earth, when the solar nebula was only beginning to gather and the atoms that would later become rock, ocean, technology, and living matter were still being sorted into place. Earth's hidden inheritance is not spread evenly through the planet, and that unevenness is part of why its origin is easy to miss. Gold gathers in veins, grains, and deposits shaped by fluids moving through rock. Platinum hides in particular igneous settings and ancient ores. Rare Earth elements appear in minerals whose names are less familiar than the technologies they later support. Uranium and thorium sit quietly inside crustal rocks, releasing heat through radioactive decay across geological time. Iodine enters oceans, sediments, and living chemistry in trace amounts, while molybdenum becomes part of enzymes that help life manage nitrogen and other essential reactions. These substances do not look related on Earth. They belong to different minerals, different industries, different biological roles, and different human meanings. Yet many of them share a deeper ancestry in rapid neutron capture, and that ancestry reaches back to debris thrown from compact stellar collisions before the solar system was born. The planet is therefore not merely built from dust in a general cosmic sense. It is chemically layered with the aftermath of rare events, some so violent that their products had to escape the edge of a newborn black hole before they could ever become quiet components of stone. When Earth formed, it did not assemble from pristine matter. The solar nebula had already been enriched by older generations of stars. Some atoms came from the Big Bang itself, especially hydrogen and helium. Many others came from stellar burning and supernovae, including much of the carbon, oxygen, magnesium, silicon, sulfur, calcium, and iron that make planets and bodies possible. The heaviest rapid neutron capture elements entered this mixture as a smaller but crucial contribution. Their total mass in the solar system was tiny compared with hydrogen, oxygen, silicon, or iron. Yet their significance is not measured by abundance alone. Uranium and thorium help maintain internal heat in rocky planets, influencing mantle convection and geological activity over time. Heavy metals shape planetary differentiation, ore formation, and the later possibilities of technology. Trace elements participate in biology not because they are abundant, but because their chemical behavior allows them to assist reactions that lighter elements cannot easily manage. In that way, a rare nuclear pathway becomes part of the ordinary function of a planet. The journey from merger debris to Earth required many transitions. Newly formed R-process nuclei first had to cool and survive in the expanding ejecta of a neutron star collision. Some were stable enough to last indefinitely. Others decayed into daughter elements while still moving through interstellar space. The debris then had to mix into the galaxy, perhaps as gas. Perhaps partly as dust grains carrying heavy atoms into colder clouds. Over time, enriched material joined the molecular cloud that collapsed to form the Sun. Inside the protoplanetary disk, dust collided and stuck, forming larger grains, pebbles, planetesimals, and eventually planetary bodies. Heating, melting, and differentiation separated materials according to density and chemistry. Siderophile elements, those with an affinity for metal, tended to follow iron into planetary cores. Lithophile elements, those that bond readily with oxygen and remain in silicate rocks, stayed more readily in mantles and crusts. Volatile elements could be redistributed by heat, impacts, and later delivery. By the time Earth had a crust, oceans, and an atmosphere, the original cosmic inheritance had been sorted through planetary physics. The atoms remained ancient, but their locations became geological. Gold shows this transformation especially clearly. Its nuclear origin may lie in neutron-rich ejecta, but its earthly concentration depends on processes that occur much later. Much of the planet's gold likely followed iron downward during early differentiation, disappearing into the core where human hands can never reach it. The accessible gold in the crust may include material added or redistributed after core formation, then concentrated by hydrothermal fluids that move through fractures and cooled in the right chemical conditions. In a vein of gold-bearing quartz, the cosmic origin is not visible. The immediate story is water, pressure, rock chemistry, and time. Yet the nucleus of each gold atom carries a history that geology did not create. Earthly processes gathered and revealed it. They did not explain why that nucleus existed in the first place. The metal stillness in a mineral is therefore a final arrangement built on top of a far older act of nuclear assembly. Uranium and thorium tell a different part of the inheritance. They are heavy, radioactive, and long-lived enough to remain present after billions of years. Their decay releases heat within Earth, contributing to the planet's internal energy alongside leftover heat from formation and differentiation. This heat does not act alone, but it helps sustain the slow motion of the mantle, the generation of magmas, and the broader thermal evolution of the planet. The connection is quiet but profound. A process near merging neutron stars can produce nuclei that later help warm a rocky world from within. The violence is separated from the consequence by immense time and by many stages of dilution, condensation, and planetary sorting. Still, the chain remains physical. Radioactive decay inside Earth is not independent of cosmic nucleosynthesis. It is the delayed settling of unstable heavy nuclei, whose creation required conditions far beyond any planet. The planet's deep heat is partly a memory of rare nuclear events. Rare Earth elements add another layer because their name suggests scarcity. Yet many are not rare in the simple sense of being almost absent. They are often dispersed, difficult to concentrate economically, and chemically similar to one another. Their complex electron structures make them valuable in magnets, screens, lasers, catalysts, and many technologies that depend on precise material behavior. Their cosmic origin is tied to neutron capture pathways, and their earthly usefulness emerges from electronic arrangements around nuclei forged long before Earth existed. This is a recurring pattern. The nucleus records the astrophysical birth. The electrons determine chemical character. Geology controls concentration. Biology and technology discover usefulness later. An element can therefore pass through several identities without changing its atomic core, first a product of a neutron storm, then a trace in interstellar matter, then a mineral component, then an industrial material, then part of a machine used to study the sky that made it. Some R-process contributions are biologically intimate without being abundant. Iodine, though not solely described by one nucleosynthetic path in every isotope, is essential in thyroid hormones that regulate metabolism in many animals. Molybdenum participates in enzymes central to nitrogen chemistry, helping life handle transformations that simple organic molecules cannot manage alone. The fraction of body mass made from very heavy merger-borne material is tiny, almost vanishing by ordinary measurement. But smallness does not mean insignificance. Life depends on select atoms because of what they can do, not because they dominate the body's mass. A human body is mostly oxygen, carbon, hydrogen, nitrogen, calcium, and phosphorus, built mainly from more common cosmic processes. Yet within that familiar chemistry sit traces of heavier inheritance. A minute amount of matter may have once been part of neutron-rich debris fleeing a compact merger. The body does not know this history. Its cells use the atoms according to chemistry. The origin belongs to physics, hidden beneath function. This hiddenness is why the story can seem almost too large for the objects it explains. A ring, a circuit, a mineral sample, a medical isotope, a grain of dust, and a molecule inside a living cell do not look like fragments of stellar catastrophe. They appear local, practical, and ordinary. Their meanings are human or geological. But matter is not limited to the scale at which it is currently used. Every atom has a formation history, and the heavier the nucleus becomes, the more selective the history often is. The origin of gold is not grand because gold is valued. Gold became available to value because the universe had already performed a rare nuclear act. human desire enters late. The atoms themselves were ancient long before they became currency. Decoration, circuitry, or symbol. Their cosmic rarity is older than every cultural meaning attached to them. Earth's inventory of our process material also reminds us that planets are not isolated endings. They're collection points. A rocky world gathers contributions from many astrophysical channels and then conceals them inside a single surface. The crust does not label which atoms came from which stellar source. The ocean does not separate its nuclei by cosmic ancestry. A living organism does not distinguish between carbon from an old stellar wind and iodine from a path that may include rapid neutron capture. Planetary matter is blended matter. Only through spectroscopy, isotope geochemistry, meteorite studies, nuclear physics, and gravitational wave astronomy can the mixture be unfolded into its origins. The ordinary world becomes intelligible as a composite record, with each element group carrying a different kind of memory. In that composite record, neutron star collisions occupy a particular place. They are not responsible for most matter by mass. They are not the source of the elements that dominate daily life in volume. Their role is narrower and more exquisite. They supply many of the heavy nuclei that ordinary stellar burning cannot easily reach, and that common supernovae may not produce in sufficient amounts. They add the dense end of the periodic table to the raw material from which planets form. They give worlds some of their hidden heat, some of their rare minerals, some of their most valued metals, and some of the trace chemistry that later life and intelligence can use. The inheritance is quiet because it is diluted. It is powerful because it is specific. The chaos of a merger becomes a small but lasting part of Earth's order. By the time these atoms rest in rock or move through living systems, their violent origin has been almost completely erased from appearance. No glow remains. No gravitational wave can be recovered from the metal itself. The event has become chemistry, geology, and biology. Yet the chain can still be reconstructed. From compact stars to our process ejecta, from interstellar mixing to meteorite clocks, from the solar nebula to the crust beneath human feet. That reconstruction gives the final movement its meaning. The universe does not remember only through light travelling across space. It also remembers through matter that survives, settles, and eventually becomes capable of asking where it came from. The memory of a neutron star collision does not remain in one form. At first, it is motion written into space-time, a rising gravitational wave signal produced as two compact remnants spiral toward contact. Then it becomes light, a kilonova spreading through the debris as radioactive nuclei decay and the expanding cloud changes colour. Much later, after the glow has vanished and the waves have crossed into distances no instrument can recover, the same event may remain as chemistry, hidden in meteorites, rocks, oceans, machines, and living cells. This layered memory is what makes the birth of gold more than a single astrophysical episode. It is a chain of translations. Gravity becomes a waveform. Nuclear instability becomes heat. Heat becomes light. Debris becomes dust. Dust becomes planets. Atoms become evidence. The collision itself is brief, but its consequences move through time in forms that look unrelated until science patiently connects them. In that connection, chaos does not disappear. It becomes legible. A detector on Earth does not feel a neutron star merger as force in the ordinary sense. The passing gravitational wave stretches and compresses space by an amount smaller than the width of an atomic nucleus across the length of an instrument arm. The signal is almost absurdly faint by the time it arrives, yet its shape preserves the rhythm of the last orbit. It rises as the stars move faster, then ends as the separate bodies merge. This is a new kind of astronomy because it does not begin with light. It begins with gravity itself. carrying information from regions where matter is too dense and too fast-moving for ordinary images to resolve. The waveform identifies masses, orbital decay, and sometimes hints of tidal deformation. It tells of bodies made not from gas like ordinary stars, but from nuclear density matter held just short of black hole collapse. In the birth of heavy elements, the gravitational message supplies the opening evidence. It says that the forge existed and that the collision happened. Light then answers a different question. A gravitational wave can reveal the merger, but not by itself the fate of the matter thrown away. For that, the sky has to be searched quickly, because the electromagnetic signal changes fast. The kilonova marks the place where the invisible dynamics of compact objects become visible as expanding debris. Its early colour, its rapid fading, its later red and infrared glow, and its spectral broadness all speak indirectly of neutron-rich material. The light is not a simple lamp shining from a surface. It is radiation escaping through ejecta whose opacity depends on newly formed heavy elements. The more complex the atoms, the more strongly they can trap and reprocess photons. Thus the debris announces its composition partly by making the light harder to escape in familiar wavelengths. The event becomes a self-filtering signal. It tells its story through what it reveals and through what it obscures. This is a fitting signature for heavy element birth, because the nuclei themselves are formed along hidden pathways far from stability before settling into forms that later appear ordinary. Meteorites bring the same story into another register. They do not show waves or fading colours. They preserve ratios. Their evidence is slow, mineral, and retrospective. Daughter products of extinct radioactive isotopes offer a record of atoms that were alive, in a nuclear sense, when the earlier solar solids formed. The old solids do not know that their parent isotopes may have been created in a nearby merger before the Sun existed. They simply hold the chemical consequences of decay. But when measured with enough care, those consequences point back to a source that supplied up-processed material within a limited interval before solar system formation. The time gap is not vague mythology. It is constrained by half-lives, isotope ratios, and models of how rare events enrich the interstellar medium. The meteorite becomes a clock whose hands have vanished but whose shadow remains on the dial. Through it, an ancient collision becomes part of local history, not because its light can still be seen, but because its atoms entered the cloud from which the solar system condensed. Each form of evidence has limits. Gravitational waves may identify a compact merger, but cannot alone inventory every element made. Kilonova light can show neutron-rich ejecta, but cannot always isolate each species cleanly, because heavy element spectra are crowded and blended. Meteorite isotopes can constrain timing, but depend on production models, mixing histories, and early solar system processing. The strength of the modern story comes from convergence rather than from a single perfect proof. Different messengers, each incomplete in its own way, point toward the same broad sequence. Neutron star binaries exist. They lose energy through gravitational waves. They merge. They eject neutron-rich matter. That matter undergoes rapid neutron capture. Its radioactive decay powers kilonova light. Some of its products survive, mix into galaxies, and enter later planetary systems. This sequence is not guessed from one clue alone. It is assembled from physics that spans nuclear reactions, relativity, stellar evolution, spectroscopy, and isotope geochemistry. The birth of gold therefore becomes a rare example of cosmic reconstruction across almost every scale available to science. The scale range is almost difficult to hold together. The process begins inside nuclei, where protons and neutrons rearrange through captures and decays. It also depends on objects more massive than the Sun compressed into city-sized spheres. It sends gravitational waves across millions of light years. It enriches clouds that may later stretch across many trillions of kilometers. It leaves traces in meteorite inclusions small enough to rest inside a hand. It becomes part of planets whose crusts concentrate elements through fluids, magmas, erosion, and time. At every stage, the same atoms are carried into a new context. A nucleus made in a neutron-rich outflow later behaves according to chemistry. A chemical element later behaves according to geology. A mineral later becomes a sample later becomes an inference. The universe does not preserve memory in one language. It preserves it in whatever physical form can survive the next transformation. This does not make the story simple or fully closed. The exact balance between neutron star mergers and other rare sources remains an active scientific question. Some unusual supernovae may contribute to parts of the R process inventory. Different mergers may produce different yields depending on mass, spin, remnant lifetime, magnetic fields, and neutrino exposure. Galactic mixing is uneven, especially in the early Milky Way. The first generations of stars record chemical scatter that still asks for careful interpretation. Even within a single kilonova, the ejecta can be divided into components with different histories and compositions. The broad outline is strong, but the detailed map remains unfinished. That incompleteness matters because it prevents the story from becoming a legend in scientific clothing. The evidence supports a powerful conclusion, but it also keeps its uncertainties visible. Gold has a likely birthplace in neutron-rich cosmic catastrophe, yet the full family tree of every heavy atom remains more intricate than one event type alone. The calmest part of the story may be its final transformation. Atoms born near the edge of black hole formation can later settle into matter that seems entirely removed from chaos. They can lie inside ancient rock, dissolve into seawater, enter biological pathways, strengthen magnets, carry electrical signals, or sit in a ring whose surface reflects room light. Nothing in their ordinary behavior reveals tidal arms, neutrino winds, fission cycling, or radioactive heat. The violence has been absorbed into stability. This is not erasure. It is the way matter changes scale. A nucleus does not remain dramatic because its birth was dramatic. It becomes part of whatever system later holds it. The universe is full of such quiet aftermaths, where extreme events leave products that no longer look extreme. The most enduring relics are often not bright remnants in the sky, but stable atoms doing ordinary work. In the end, the birth of gold and chaos is also the birth of continuity. A merger destroys a binary, may create a black hole, and sends debris outward under conditions that briefly undo the familiar order of matter. Yet from that disorder comes a set of nuclei capable of lasting longer than stars, crossing interstellar distances, entering planetary disks, and becoming part of worlds that did not yet exist. The event is catastrophic locally, but generative chemically. It removes two neutron stars from the universe as separate bodies and adds something to the inventory of future matter. Gravitational wave detectors, telescopes, and meteorite laboratories do not merely describe different chapters. They show that the same physical event can be remembered in space-time, in light, and in stone. That is the deeper meaning of the chain from neutron star collision to Earth. The cosmos does not only create through steady burning or quiet accumulation, sometimes it creates by breaking its densest remnants open, letting their compressed matter rush outward, and allowing instability to cool into substance. Gold is one of the still forms left behind by that passage. Chaos is not its opposite. Chaos is part of the route by which it came to rest. The story settles where it began, inside matter that seems ordinary until its history is followed backward. A heavy atom resting in rock does not announce the pressure that shaped it. It does not carry the brightness of the kilonova, the strain of space-time, or the brief nuclear storm that changed neutrons into protons and instability into form. It simply remains, held inside chemistry, patient enough to pass through clouds, planets, minerals, oceans, and bodies. That quiet endurance is part of what makes the origin so profound. The universe does not preserve all of its most powerful events as visible monuments. Some vanish into distance almost at once. Their light fades, their waves move on, their remnants cool or collapse. Yet a fraction of their substance escapes, and in that escaping matter, the event continues without spectacle. It becomes a trace isotope in a meteorite, a rare element in a crustal vein, a source of planetary heat, a tool for human instruments, a small hidden part of living chemistry. Science does not make this chain less mysterious by explaining it. It gives the mystery structure. It shows where the certainty is strong, where the models still have edges, and where the next observation may refine the story. The birth of gold is not a myth of preciousness added to the sky. It is a physical sequence, severe and delicate at once, in which collapsed stars give back a little of their hidden matter before gravity closes around the rest. What remains is not chaos forever. It is order carried forward by atoms, quiet enough to be overlooked, durable enough to remember. In that stillness, the collision has not truly disappeared. It has only changed language from waves and light into the calm persistence of matter.